Alright, greetings to everyone. Today we are going to look at diagonal relationship. My name is Joshua Tumwini. So, diagonal relationship is the similarity in the chemical properties between elements in period 2 majorly to their diagonal neighbors in period 3 and the adjacent groups. That's the definition. So, the focus is always put on the following. You've got to know that it is all about the similarity. The similarity in what? In chemical properties between what? Elements in period 2, their diagonal neighbors in period 3, and of course the adjacent groups. I'll just give a small clue on this, and we have already lithium with magnesium. Let me assume that is my magnesium. And we have beryllium, and we have aluminium here. I'll talk about something small here. Then we have boron, and then silicon. These are the examples of those particular elements which have similarities in chemical properties. Now, when you look at this, if I'm to draw a line here, you realize that this is period 2, and then this is period 3. If you go for groups, this is group 1, this is group 2, this is of course even this one is part of group 2, so it is just around here. Let me even change it and I put it here in group 2 like that, and then we go for group 3 here, which is supposed to be around here, that group 3. So this is where we're having also boron. So I'm just going to show you something small and you see what I'm trying to mean. And this is group 4 here. Let me try to rub a few things that I've just put to help us understand even better. So we are having, this one is not there, we are having something that looks like that. And of course now silicon is going to be under group 4. Everybody knows that. So we are having silicon around here. We know very well that here there is carbon, but we're not much interested in carbon. So the diagonal shape we are talking about, when they talk about chemical properties being similar between elements in period 2, we mean these particular elements, these ones here, and their neighbors in period 3, which is this particular period here, and adjacent groups. Adjacent groups, this is the first group, and this is the second group. So you find that adjacency is something of this nature, not just directly the opposite. This is adjacent. So these two, lithium and magnesium, have similar properties. And then we go also for beryllium and aluminium. Beryllium is in group 2 and aluminium is in group 3. They also have similar properties. And when you go for boron, like that, then that is also another group of elements that exists in the same kind of, with the same kind of behavior. So that is it. But let's move on and you see what I'm trying to mean here. Like we've said, we have the pairs lithium and magnesium. We saw it formerly. We have beryllium and aluminium. This one is group 2, it's group 3, it's group 1, group 2, and then we have the last one, which is boron, and then silicon. We shall talk about ore if time allows. Now, these particular elements have that kind of a behavior of behaving just like their neighbors, like I've already told you in the former description, and we expect them to have the following, to be the following reasons why those properties are like that. One, they usually have similar polarizing power, or what we call the charge density, and this is brought about by a very small atomic and ionic radius as compared to other group members. So they have similar electronegativities, they have similar electropositivities, they have similar electrode potentials. So these are the reasons to why we expect actually those particular elements to exhibit diagonal relationship. That's the major reasons. Now we have chemical reactions in which particular elements are similar, but we have the reasons why they are similar. So you should always differentiate. And let me just try to elaborate it here. If a person says, why, then they want the reason, the reasons. So that's when we talk about these issues. But if they say, in what ways, then that's when we look at the chemical reactions, or the behaviors in that case. So you should note the why, which is always the reason to why these chemical reactions happen, and in what ways. You should always differentiate. If you don't differentiate those, then you're already in trouble. You just have to be very, very careful. So we move on. Now we're going to look at different properties of those particular elements which exhibit diagonal relationship. Similarities in chemical properties. Let's start with lithium and magnesium. I'm just going to try to be very slow so that you get the real picture behind all these issues. Both react with nitrogen on heating, and then they form for us the nitrides. Let me not waste time on this, but for elaboration, we can do that. If I have lithium, and it is a solid, everybody knows that, and it reacts with nitrogen, that is when the two are heated. This is a gas, one of the most inert gases. It doesn't easily react, but in this case it will react, and it forms for us lithium nitride. Lithium is in group 1, so it is having valency 1, and nitrogen is in group 5, and it's having valency 3, and this is a solid. So it is a nitride called lithium nitride. Now if I want to balance, I can see that this is just having nothing, and this one has a 2, so I will put here a 2, which will change lithium to 6, and I put here a 6. So that is the first case. But also the same, if it is now magnesium, the same issue happens. So the magnesium, which is also a solid, that is in group 2, unlike lithium, which is in group 1, reacts with nitrogen in the same way, and it is still a gas, it will not change, and it will give us automatically magnesium nitride. Now in this case we have to exchange the valencies accordingly, so it's going to be giving us here a 3, and then the nitrogen is going to be getting a 2 because magnesium has the valency of 2. That is it, and it is still a what? A solid. Now nitrogen is already balanced, so magnesium is the one which is not balanced, so I just have to put here what? A 3. That is what I'm trying to mean. So you must know that every single time you mention a point, then you have to write its equation, if at all it exists. We go on. Don't worry about that. They are hydrogen carbonates. Hydrogen carbonates, let's say lithium hydrogen carbonates and magnesium hydrogen carbonate, they exist in solution. I'm going to compare. You know very well that hydrogen carbonates of group 1, for group 1 hydrogen carbonates, usually they are in solid form. Solid form. But then those ones of group 2, if they are hydrogen carbonates, they are in solution form. So now this lithium usually tends to have the same behavior like magnesium, so the behaviors of group 2. So we expect their hydrogen carbonates also to exist in solution. So lithium, unlike sodium hydrogen carbonate and potassium hydrogen carbonate and others, as you move down, which are usually solids, this one is always going to be a solution. We go on. Both form normal oxides when heated. We know very well now in that case we are going to be forming normal oxides. Remember, away from this, if it is group 1, other members, group 1, they can form normal oxides, and they can also form peroxides when heated with excess air. But as you go down the group, then you can even form the super oxides. That is for group 1. What is surprising is that this lithium you're seeing here, it only forms the normal oxides. Because we know that lithium forms lithium oxide. But when it is potassium, it can form potassium oxide, it can form potassium peroxide, it can form potassium superoxide, and many others as you move down the group. So I'm not, let me give just one equation, that lithium, which is already a solid, will react with oxygen, whether it is excess, whether it is limited, it doesn't matter. And then we expect this particular lithium produce for us lithium oxide. This is a 2 here now, and O, and this lithium oxide. Then you can balance it. You see here we have a 2, here we have a 1, so we put here a 2, giving us here a 4. So it behaves just like magnesium, because now for group 2 members, in fact this is what they do. For them, they don't form any other oxide apart from a normal oxide, whether it is excess, that is limited. So we expect this one to give us also a magnesium oxide. Please don't worry about the symbols, because the pen I'm using is just a mouse. To balance. When you don't balance your equations, just be assured you will not get any single mark. So we go on. Alright, there are hydroxides sparingly soluble in water, including their carbonates. And we know very well that group 1's group 1 hydroxides are very soluble, and group 1 carbonates are also very soluble. But this time when it is lithium, they are sparingly soluble, so they are not so soluble. So they behave exactly like those ones of group 2, that is magnesium. Carbonates and hydroxides decompose on heating. And I want to look at this critically. I want to give just examples and a few of them. Carbonates, if you look at sodium carbonate, I'm just trying to compare. Maybe potassium carbonate. I want to give you a clue from O level. We say that these ones are sorry, do not decompose on what? On heating. But then when you look at lithium carbonate, for it is behaving just like group 2 elements, and for it decomposes to give us lithium oxide, and then it gives us also carbon dioxide. Normally, this is something that is a little bit funny. Carbon dioxide is just a 2 here. It is a gas just like that. So that is your lithium. Of course, automatically even magnesium does the same because it is already in group 2. When you go on to the next, nitrates decompose on heating and give oxides and nitrogen dioxide. Look at lithium. Unlike other, so we have lithium nitrate decomposing to give us lithium oxide, and it gives us nitrogen dioxide, and it gives us also oxygen. Remember, if it was, for example, sodium nitrate, it would be decomposing to give us instead the nitrite, sodium nitrate, just like that, and of course the oxygen gas. So this one is defying all the odds. This one here, it gives us instead the round. You make sure you balance. I am leaving all these areas unbalanced intentionally. If you're making those notes, please do what? You balance. Halides except fluorides and whatever are soluble in solvents, the organic solvent. Now let's go to something else, beryllium and aluminium. Oxides and the hydroxides are amphoteric. If they are amphoteric for real, how do I represent something that is amphoteric? That is one way, and that is beryllium hydroxide giving us berylate ions when pressed with sodium hydroxide. But aluminium, it can also give us aluminate ions. But you note what I'm going to do. Instead of this, I can say, instead of beryllium here, I can also write it just like this. Beryllium hydroxide, it doesn't change the formula here. You have something like this. It reacts with the hydroxide ions, which is the sodium hydroxide in that case. And then it gives us, now instead of this formula, you can write this. Actually, it's the commonest in textbooks. Be or 2, then 2 what? Minus. Berylate ions. It's still the solution, because once you talk of the ions, in that case you already know the solution. But this time we have some water this side produced as that. So your work is to balance, and you look at the charge is here 2, so I can put here 2 like this, 2, and then I put also here, and everything has balanced. But instead of writing the berylate ions, I can write there sodium berylate. It's just like that. Then hydroxide is just like that. Okay. No, sorry for that. Just like that, and it's still what? A solution. This is called sodium berylate. Then instead of this, I can still write sodium here with a 2 because of this particular 2, and it becomes just like this, or 2. So everywhere you see the sodium hydroxide, where is hydroxide ions, I just put there sodium hydroxide, and that's it. That is how we write the equation in that particular case. So you've got freedom to write either this or this. It's your choice. It's your choice. When it is aluminium, same issue. Alternative for this is always going to be aluminium, just like this, but this time it's just a single minus, and then we have also some water being produced. But all this is a solution, while water is a liquid. Let me just even complete this equation. So we are having hydroxide ions behaving like this from aluminium hydroxide, like that. It will not change any single thing. So your work is to balance. But if you check properly, you realize that it is only hydrogen that is not balanced, so, and of course oxygen. It must be 4, so I put here 2 and everything is balanced, like that. So this is an alternative. So we have either this or this one, but all of them mean the same. So in the same issue, sodium hydroxide. Then here, same issue, sodium aluminate. Aluminate, which is written just like that. Then even this one, and this one is like sodium aluminate. So the aluminate ions have 2 formulae. You just have to know when to use what. If you have to use the last one, this number 2, if you want to use this number 2, then just know the water is going to be put the other side, on the right. But when you have to use number 1, then there is no water the other side. You can move. However, you can also look at the oxides. I don't want to the oxides. If it is beryllium oxide, same issues happen. You can use the simplest methods with hydroxide ions. It will give us still the berylate. Berylate, you said it has got 2 formulae. I'm not going to write both. I'll write just this one. And in this case, you still produce water. So every single time you write that particular formula, for that one you have to produce alongside water, because it cannot balance. We have, because of this hydrogen on the other side. Then you balance it by putting here a 2, which gives us 3 oxygens, and everything is balanced. If it is aluminium oxide, that's how it is written. So that one is going to still react with hydroxide ions, like that, and then it gives us aluminate ions, O2 here, minus, which is still a solution, and then you also produce your water, like that. So we are having that. You can choose now to balance. You just, if you check so well, you may find one it is even already balanced, but I don't think it's balanced. We are having 2 aluminiums. Maybe I can put here 2 and a 2 here. If I put here 2 and I put a 2 here, I think it balances. I'm not sure. I think it balances. Okay? Those are the 5 oxygens and everything is balancing. So that's how the oxides and the hydroxides react with sodium hydroxide. But now if it is, when we talk of the word amphoteric, it means they can also react with acids. But because I know, as you know, what happens, I don't need to waste time on that. But anyway, giving only one example, beryllium oxide, you should just choose one acid, reacts with HCl. You don't need even to heat at all. Body form, you're going to be forming beryllium ions or beryllium chloride, which is still a solution in that case. And then you have the water, because this is the hydroxide, should be able to give us a salt and water. I don't want to waste time on that. That is it. You balance accordingly. If you don't want to do this, you just use hydrogen ions. And of course, it's very dangerous for you to use a particular acid. You just write the ionic equation by just telling us, this is an oxide. So it is reacting with the acid, because now this one is already telling us it is an acid. You don't want to specify which acid, because someone is going to say, oh, who acid to talk about which acid. And then you'll be able to form beryllium ions. Beryllium ions and water. It looks like that. If it is aluminium, you know what really happens. Aluminium oxide still reacts with the hydrogen ions, and it's going to be giving us the aluminium salt. So aluminium ions, and you still form what? Water. So I'll have to look for a way making sure that everything has balance. So the oxygen is this side 3, so I have to balance the oxygen here as 3, giving us this one as 6. So I'm going to put here 6. When I put here 6, automatically aluminium is still 2. For you to balance those charges, you put here the 2, so that the charges are 6. That's how we can write that particular equation. And I think I'm not being mean. Everything is very, very clear. I don't know what I'm forgetting. Let me move. Conditions. So now we're looking at the metal itself. The metal of beryllium and aluminium will always react with concentrated and hot sodium water. So these are always the conditions. Every single time we're talking about sodium hydroxide, you always put that it is hot and water and conc. And it forms for us a complex, which is still the other original complex we're dealing with, and hydrogen gas. Like you're going to see. That is it. But we've already agreed that the complex has got different formulae. You can have this O2, 2 minus, and still, if it is this one here, it has another formula of this nature still, 2 but minus here. So if you look at the O-level chemistry, it's not really close to this particular chemistry. You have to be very, very careful. But once you form that, then when you produce hydrogen, it doesn't move alone. It has to move with water, just like that. But of course now in this case, you know, you're having water here, so there's no need for you to put it the other side. Okay, can we move? Right. Their chlorides and bromides are covalent and they diamize in vapor phase. So we are having all those. I don't need to waste time on that. They both form ionic carbides, which hydrolyze form methane. You can see this one is forming for us methane. This is called methane. and the hydroxide ion is also formed. When it is also aluminium carbide, it forms for us the same thing. Unlike calcium carbide, for it's going to be forming for us ethine on hydrolysis. So hydrolysis is addition of water, hydrolysis. So ethine, for it is always C2H2. But calcium is in the same group as beryllium, but beryllium is refusing to do what calcium can do. For it is choosing to do, let me first change this, it is supposed to be here. It is choosing to behave just like the aluminium. I think you've seen what is happening. So that's the case for every single thing. I don't want to waste time on this because I am very sure you can see what I'm trying to mean. We know very well that both are rendered passive by conc nitric acid, though the dilute can somehow react. And you know the reason is because of formation of impenetrable oxide layer. Both form stable fluorocomplexes, like one of those that I've just given there.